Today's lesson is going to be about energy. So let's talk, and we'll use some terms we've heard before. Let's pick an element first. All right. So I'm going to give you an element here, and there we go. And that is the element hydrogen. It happens to be a diatomic molecule. It's always found in groups of two. And I want to take another element. This time I'm going to take oxygen. It's also diatomic. If you remember your Hober-Finkel twins, H2, O2, Br2, F2, I2, N2, and Cl2. And this is another molecule of oxygen. It's also the element oxygen. And I can certainly mix those together. And when I mix them together, I have a mixture of elements, hydrogen and oxygen. That's probably pretty uniformly mixed. We can call that a homogeneous mixture. And then, if I were to take a mixture of the correct, what's called stoichiometric ratio of hydrogen and oxygen, and add an activation energy or a source to ignite this, that's what we're going to do. So we got a mixture of hydrogen and oxygen, and then I've got a little candle there. And when that candle goes, it goes bang, boom, explodes. The atoms are ripped apart, and then they come back together. So those molecules, there's a chemical reaction. When atoms get rearranged, here they are before, here they are after, that is a chemical reaction. And look at the new combination I formed. I formed H2O. I formed water. Now, normally this reaction is done in a chemistry room where the teacher will fill up a balloon with hydrogen and another with oxygen, and they usually make the hydrogen balloon twice as big as the oxygen because we want a 2-to-1 ratio. Then they hold the two balloons next to each other, and then they have a long stick and they light a match and it goes boom, and it's really, really, really loud. Now you might think, doesn't everybody get wet with all that water? No, because it's so high energy that water has been vaporized. It's been turned to a gas. So it's not like you go to SeaWorld and you're in the first 12 rows and Shamu the whale arches over and sprays you soaking wet. It doesn't happen like that at all. All right? It's just a loud bang, and water's formed. Now, that is a compound. We said a chemical reaction, when that happens, what you produce has different properties than what you started with. Hydrogen is an explosive element. Oxygen supports combustion. Water puts out combustion, doesn't burn at all. So very different properties. I was going to show you a little video, but it's struggling to load the videos where it was going to separate out water and take water into two parts, hydrogen and oxygen. I'll go ahead and instead put a little video on the calendar, and you can watch it if you want to see that happen. This would have been the video here. Again, I'm going to skip that for right now, and I'll put it on the calendar. Perhaps you're wondering if you've ever seen, maybe you're into space and rockets and things like that. You think Tesla's a pretty cool guy, right? And in the original space shuttles, the way these things went is they were basically blasted into space by being strapped onto these propulsion rockets. So this one has twice the volume of these because it's hydrogen and oxygen. It's liquefied hydrogen, liquefied oxygen, and when they mix, they end up forming hydrogen, 2 parts hydrogen plus 1 part oxygen, water plus energy. So this smoke that you see is nothing more than a cloud. It's just water vapor being formed. Now, what happened on the Challenger, I believe it was 1986, I think April. It was very, very cold. That's one where Kristen McAuliffe was going into space, the school teacher. And there was an O-ring, basically a rubber band seal that keeps between the hydrogen and oxygen. And when rubber gets cold, as it was that morning, it loses its elasticity. You can put a rubber band in ice water and try to squeeze it, and the rubber band will break. That's basically what happened. So whatever it was, 86, 92 seconds after liftoff, they said throttle up. It's basically like you're driving a car and you pull over into the freeway, and then once you get on the freeway, you kind of got to gun it to get up to speed. Well, as soon as they went throttle up, all the hydrogen and oxygen combined and blew up. Now, Evidently, they didn't feel anything. They didn't die until they hit the water, but they would have been knocked unconscious instantaneously. So evidently, they didn't suffer at all when that happened. We've had other explosions of hydrogen. This is the Hindenburg in 1937 on its maiden voyage to the U.S. It was coming here, and it was, now if you don't know, this is a blimp. This is all lightweight aluminum ribbing with a skin of cloth that's been impregnated with what's called a material called thermite. Thermite has an incredibly high ignition temperature, but once it starts burning, burns incredibly hot. Now, it's unsure of what happened, but we know the result of what happened was it crashed and it blew up. I'm just going to play this video. We'll see if this one plays for you.
Nearing the fatal end of her first Atlantic trip of the season, the Hindenburg approaches the mooring mast at Lakehurst. 21 of these sky voyages the world's biggest dirigible has made, so safely, so surely that the experimental service has become a matter of routine. Scarcely 100 feet above ground, the giant airship with her framework encasing 7 million cubic feet of inflammable gas is being carefully maneuvered towards her hangar, when suddenly...
All right, so we get the general idea of what happened to the Hindenburg. And again, it was full of hydrogen. They're not sure what happened. It could have been, you know, in those days, men had shoes. They would wear out, and they would get them repaired. And on the bottom of the shoe, they would put a little piece of metal. And it could be that the passengers were down below, that one of the stewards was climbing up on the framework going across to make a shortcut. Could have been a lightning strike. Nobody really knows for sure what caused that to blow up and for people to die. Nowadays, the blimps we use are a little bit different. This one was filled with hydrogen, and if you've ever seen the Goodyear blimp, it's much smaller, and it's filled with helium. Helium is inert, will not burn, and the people are just down here. I think it only holds maybe 6 or 8 people total in a Goodyear blimp. So very different. Blimps nowadays will not blow up from the gas inside. And so again, lots of stored energy in chemicals. So we can see electrolysis, separating water into hydrogen, oxygen, causing an explosion, you know, lots of things. So we want to examine some of the properties of elements as well, and the thermodynamics, the energy changes that they undergo. There's different types of energy. I've listed a few here. Radiant energy, like radiation, energy from the sun. My skin is an excellent collector of radiant energy. I had red hair and really white skin, and I go out, I get sunburns really bad, and that's given me skin cancer more times than I would like. So there's certainly a lot of energy coming from the sun. There's thermal energy from heat. If you've ever worked around a foundry or maybe a stove, you know there's a lot of heat coming off of there. There's chemical stored energy and potential energy in a match head or in an explosive device. Nuclear energy, the atoms in the nucleus, there's energy held together by the strong force that when we release, we call that nuclear energy. Of course, there's electrical energy we see when there's lightning or when we generate it and then pass it through the electrical grid. These are all different forms of energy. Now, in terms of big picture idea, there's potential energy and there's kinetic energy. Kinetic energy is energy of motion, where potential energy is stored energy. So when we look at this person riding the bicycle right now, they might be coming up very, very fast up this little hill. And as they keep going up the hill, they are probably slowing down. So they at first have a high amount of kinetic energy because they're moving fast. And then as they go up the hill, they lose some of their kinetic energy because they're slowing down. But because they're getting higher up, they gain potential energy. At the top, they probably just about stopped up here. So now they have basically no kinetic energy, but a lot of potential energy, because if they don't do anything but lean forward, they'll start to pick up more speed. That stored energy will be released. So right at the top, they would have the most potential energy. And then as they go flying down the hill, they're going to be losing energy and picking up more kinetic energy. And when I say lose energy, understand, energy is never lost. It simply changes from one form to the other. When you burn something, the energy that was stored in the, let's say, piece of wood is released as heat and light and maybe some sound. Those are the way that the energy is accounted for. No energy is ever lost due to the law of conservation of energy. So again, kinetic energy, energy of motion. Potential energy is stored energy. If I take this little, well, let's deal with this one first. I've got an equation here for kinetic energy. It's 1/2 mv squared. Now, coaches don't inherently know this formula, but they do worry about it. If you're, let's assume you're a football player. You're probably not playing football right now with COVID, but two people that are playing linebacker at the high school level are basically going to be the same size. If one gentleman was, let's say, twice the mass of the other, they would have twice the energy, because if you double mass, you double the energy. Generally, though, players have roughly the same size for the same positions. Now let's talk about velocity, speed. See how this is squared? If I am twice as fast as somebody else, I don't have twice as much energy. I have 4 times as much energy because it's 2 squared. If I throw a football and I snap my wrist 3 times faster than the other quarterback, well, that's going to give me 9 times more power. So coaches worry about technique and form, no wasted motion. Good technique corresponds to more power. More power generally means you do better. And so that's the energy of motion. If I look at this dam here, there is, I think this is the Hoover Dam, you've got all this water behind here, and it's basically stationary behind the dam. It's allowed, though, and so it has potential energy. As it runs through the dam, as it falls over the edge, it hits a turbine at the bottom that spins, and that turbine then makes energy. So the water's motion falling down, hitting the turbines, is what makes hydroelectric power. Maybe you have a battery in your watch, well, or maybe your cell phone, because nobody wears watches anymore. Well, that has chemical potential energy, and as that energy goes out, you have to recharge the battery every day or every few days. Maybe you have an old watch that somebody gave you, and you have to manually wind that watch every 24 hours because you have to put in mechanical potential energy. Or maybe you have a grandfather clock, and you have to pull the little metal chains to pull the weights up, and then as they fall down through gravity, that's what is the mechanism that turns the clock to make it work. Again, we're seeing all of this potential energy being stored in the spring of a watch, or a battery, or the water trapped in the dam. Okay? So they're very different types of energy here in terms of what they mean. Now, if you take this object and you take it from, imagine this is a string with a bowling ball on the end. If you hold the bowling ball up to position A, what type of energy does it have while you're holding it at A? It's not moving. Good, it's potential. And when you let it go, what's it going to do? It's going to release that potential energy and become kinetic energy. And it's going to swing down, and then it's going to come back up. Will it ever make it to the same exact point as it started to on the opposite side? No. It'll be very, very close, but then over time it'll swing and it'll get less and less and less and less until it finally stops. That's because there's air resistance from the string, and that sphere, that ball hitting the air, slows it down a little bit. There's a classic trick that sometimes physics teachers do. They take a steel wire and they dangle it down from the ceiling and put a bowling ball. And then they turn sideways and they hold the bowling ball up to their chin. They close their eyes and they let go. And the bowling ball swings away and it comes right back up and it goes right up next to their chin without actually hitting them. And the key is it won't hit them if they just let go of the ball. If they push the ball, they're going to be having to run to the dentist because they're going to get their teeth knocked out. So they wouldn't want to do that. All right. I don't know. That thing is swinging away. Now, if I were to take a larger ball, C, than A, what do you think it will do? Will it have more, less, or the same amount of kinetic energy? It'll have more kinetic energy because it'll move a little bit faster due to gravity, and it also has greater potential energy the bigger the object is. Another example of this would be the Twin Towers. It took numerous years, I don't know how many years, multiple years to build the Twin Towers, to take those steel girders and bring them up 100 stories plus. And when the airplanes hit on September 11th, all that potential energy was released as that building fell down and released all of its energy into the ground. All right, kind of a sad example there, but I want you to see and think about potential kinetic energy in lots of different venues. Well, let's think about this. Which has more kinetic energy, a slow-moving school bus or a fast-moving bullet? Well, the answer is it depends, right? Like, I wouldn't want to get hit by either one of these things, but a small bullet can do a tremendous amount of damage if it's moving at a fast enough pace. Likewise, a very slow-moving bus, even if it just barely runs over you at a very slow speed, can do a lot of damage, right? So let's say that I have a bus that weighs 10,000 pounds. That's 5 tons. It's only moving at a half mile per hour. You could run the numbers there and find out how much kinetic energy it has. Or you could take a relatively slow-moving bullet, 240 miles per hour, square that times its mass, and figure out which has more energy. So both of these things are important, mass and velocity, but velocity oftentimes has a bigger effect because it's a squared term. All right. Enough on that one. Let's keep moving. All right. So let's talk about kinetic energy in particles. Now, we've talked about this when we talked about temperature versus heat, right? Remember the little bell curve? It says you've got some molecules moving very slowly, some moving very fast. That's what kinetic energy is. And so it turns out maybe this is the average. Truly the average would be more over here, but it doesn't really matter. Let's pick another object. So I've got the blue line and the red line, and this average is going to be farther over. Now, this red one is at a higher temperature because it's moving at a faster average speed. It's farther to the right. I hope that makes sense. Now, this is kind of like an education. It's really easy to get everyone to, let's say, a junior high graduation rate, right? It doesn't take much to do that. A little bit harder to get everyone to graduate from high school. And if we were to go a higher temperature, what would that graph look like? Well, I hope you tell me it would be a little bit lower and farther out. And it would come way, way over here, a little bit lower down, because it's harder to get all the molecules to a high temperature, right? If you think about boiling a pan of water, to get all the water to go up 2 or 3 degrees, it's not very difficult. But if you're trying to get all the water to get 50 degrees higher, it's actually pretty difficult. Some of the molecules will get much hotter than 50, and others won't quite get to 50. I think this is the same graphic. I don't know what happened there. All right, so let's look at this one. This is kind of showing us if you look at some iced tea and some hot tea, right? And the iced tea the molecules on average are moving slower. So if you were to add all these up, these molecules are moving slower, hence its colder temperature. And over here, the molecules in here are moving at a faster rate, but I don't get as many of them to move as fast, but they are on average moving faster. Excuse me. So that's at a higher temperature. All right, let's keep on moving here. This is trying to show you, it seems a little out of order to me. This is a touch-sensitive explosive, nitrogen triiodide. I've included a video here. I'm not going to click it. It's a really nice video. It's about 5 minutes long where they have some slow motions of nitrogen triiodide. So this is a material we make in the lab. It's nitric acid dissolving iodine crystals, and then you pour it on a piece of paper and it becomes very, very unstable. So unstable that if a fly lands on it, it will explode and detonate and be quite loud. So here we are just touching it, and these are stop frames instead of video because it's easier, just touching it very lightly with a stick. And when it gets hit, it explodes and it decomposes and it blows up all that purple gases, iodine gas vapor. So we can look at that and think about what that might look like at the molecular level. Here is some nitrogen triiodide. So the nitrogen is represented by the brown circle, and the three purple ones are the iodine. So nitrogen triiodide. Now, if you want to think about this as a very unhappy marriage, where if, I don't know, maybe it's a man and a woman, they really shouldn't be together, and anything sets them off. The guy forgets to put the toilet seat, back down after he uses the bathroom, and the wife just starts screaming at him, right? Anything's going to set this couple off. Well, that's the nitrogen triiodide. You simply touch it, you whisper at it, you go poo, and it will go boom, and it will explode, decomposing, rearranging the atoms into nitrogen gas. Remember, nitrogen is one of the Hoberfinkel twins, N2, and iodine gas, I2. That's another diatomic. So there's a chemical reaction with a rearrangement of the atoms. There's also energy released because this is an exothermic reaction, or also called an exogonic reaction, because the energy is leaving. If I use exothermic, I'm referring to heat leaving. If I say exogonic, I'm referring to energy. Energy can be in any state: heat, light, sound, and so on. Generally, the ACT, SAT will use exogonic and endogonic instead of exothermic and endothermic to be more encompassing. All right, well, let's use those terms, exothermic and endothermic. If I'm looking at an energy profile. So over the time of the reaction, the reactants, what I started with, had a certain amount of energy. It's up here. Then after they react, they end up with only this much energy. So they released energy. So the reactants turned into products, and they gave off energy. If something's leaving, look at exo, kind of looks like the word exit sign. You're leaving. Or maybe you remember from biology, we have a skeleton on the inside of our body, but things like lobsters have their bones on the outside. They have an exoskeleton, right, on the outside. So exo refers to something leaving. And in this case, the products have less energy, so we released energy. I'm going to use the term delta H, or change in heat. Now, the H for right now means heat. Later on, we'll learn that it's a thermodynamic state function called enthalpy. But if you want to think of it as heat leaving, that's why it's a negative. It's going away. If heat was going in, it would have a sign convention of a positive delta H. So when we look at energy, we always look at it from the perspective of products. The product is losing energy, so it's a negative delta H. Now, let's pretend that I read the energy at the reactants had 10 units of energy, and at the products they have 8 units of energy, right? That would mean that they must have lost 2 units of energy, because energy is still conserved. Law of conservation of energy. If you start with 10 units of energy, you have to end with 10 units of energy. Energy is never lost. It's always conserved. Now, if I look at an endothermic reaction, what do you think that profile is going to look like? Okay, I think what I heard you mumbling over there was it's going to start low and it's going to end at a higher amount because energy is going to go into the reactants, and you are 100% correct. So here's the energy of the reactants. Here's the energy of the products. So we have to add energy in. So from the products perspective, energy was added, so plus delta H. Now, why did it go higher? Well, we'll talk about that little hump to get done there. All right, we'll talk about why it had to go a little higher in just a bit. Okay, that's called its activation energy. Activation energy is the minimum amount of energy needed to start a reaction. Now, the example I always give in class is this. Let's say your mom says, clean your room. And you, being a typical teenager, just ignore mom completely. And then she says it again. And finally she says it a third time in a very loud, shrill tone using your full name, including your middle name. At that point, you know you are in trouble and you better go up and clean your room because that's the minimum activation energy required. Yelling, middle name, you better do it or there's going to be consequences. Okay? So if I were to light a match, if this is the match, and I just barely rub it against the side of the box, it's not going to light because I'm not adding enough activation energy. I have to hit it pretty hard to get it to activate, to get that correct activation energy. That's what we mean. Now, maybe you've heard of a catalyst. A catalyst is something that speeds up a chemical reaction. So if I'm trying to go from reactants to products, I think of this as driving a car over a mountain. Right? I got to drive all the way over the mountain and then I can coast down. And it might take me 3 hours to drive over that mountain. Now, if someone were to drill a hole through the side of the mountain, make like a tunnel, then I could go from here, drive through the tunnel and over to the other side in like 20 minutes. Well, that is a game changer, right? A catalyst speeds up the reaction. It's not a reactant. It's not a product. It's a pathway to get to where you're trying to go to. You have something called a catalytic converter in your car that takes the carbon monoxide gas that your car is generating and it converts it quickly into carbon dioxide gas that comes out the tailpipe. Right? That's what it's doing. Catalysts speed up reactions. If I'm a chemist and I'm doing a chemical reaction that takes 3 hours, and you give me a catalyst and I can now do the reaction in 15 minutes, I can now be much more efficient and make you a lot more money. Now, even if that catalyst costs $10,000, it probably lasts 2 or 3 years and can be used over and over and over again every single day. It is well worth it. Oftentimes, catalysts are made of platinum. That's a very expensive metal, but the cost is sort of irrelevant because of how much faster it makes things occur. So, to review, the activation energy is the energy it takes to go from the reactants up to the very top of that hill so that it can get to and turn to products. Okay? So the minimum amount of energy needed to start a reaction is called the activation energy. So without a catalyst, this dotted line is the activation energy. If we add a catalyst, then it's going to be a pathway to lower the activation energy. It's going to allow me to go only over here than up over the top. So think of it as a pathway. I could give you some other examples. These might be a little silly, but if you've ever played pickup sports like flag football with your neighborhood, inevitably somebody gets in an argument about something. If you have a referee, then the referee steps in and says, you're right, you're wrong, and the game continues. If there's no referee, the arguments just go on and on and on, and nothing happens. Or maybe on the dating scene, when you become 21 plus, you might go to a bar to meet people. When people are a little bit drunk, they tend to, be a little friendlier than when they're not drunk. So I guess alcohol might be a catalyst for dating. Who knows? Just a silly example. So a catalyst then lowers the activation energy and makes a reaction occur more quickly. Let's see, this is probably the same diagram, we're just going to label it again. So is this endothermic or exothermic? Reactants are here, products are here. So products have less energy, so it released energy, so it is exothermic. Good. Okay. So when we look at this, reactants always go here, products go here. That difference between reactants up is activation energy. It's called the activated complex. You don't need to know that term. If I were to add a catalyst, though, it would lower the activation energy. All right. Let's talk last now here about different energy sources. Maybe you've heard the saying, don't put all your eggs in one basket, right? That's an important thing. Don't define yourself by one thing, like I'm a great basketball player, and then you get injured and you think your life is over. Or you decide to buy a stock and you say, I'm going to buy Sears stock because Sears is a company that's going to be around forever. And then you realize you've lost your whole life savings because Sears stock isn't worth anything anymore. Well, let's look at energy. And this is in the United States. Back in the, and you don't need to know this, I'm simply kind of giving you some background information. In the 1850s, wood was plentiful. And we got more than 90% of our energy from wood, and the rest we got from coal. By the 1900s, we had changed our energy use quite a bit. We were now building homes and not burning down trees to make energy. We found other uses for that wood. And we found coal was plentiful, and we were burning a lot of coal in 1900. Right, and the Industrial Revolution to make steel and everything else. And we started to add petroleum and natural gas. Now, we certainly didn't have any nuclear power in 1900, but we were starting to build dams, hydroelectric. By the 1940s, we had simply stopped using wood for energy for any real amount. And we had a pretty good balance. We were using coal, and we're using more petroleum and natural gas and building more dams. We still didn't have nuclear energy by 1940, but we had a pretty decent balance of our energy profile. And then by the 1980s, we got hooked. We were like hooked like a druggie on oil. And 70% of our energy came from oil. And a lot of that oil came from the Middle East. And there were embargoes, and that was a problem. The cost of oil, cost of gasoline would go to the equivalent of, $5 to $7 a gallon by today's cost of living. And if you look at the cars in the 1970s and 1980s, they were big gas guzzling cars that only got 15 miles per gallon. So that was very painful. And we weren't using very much coal because we learned that coal was dirty and was polluting the environment. Well, by the 1990s, we had figured out that we could actually do a chemical reaction and put what's called a scrubber on the coal burning smokestacks to absorb a lot of the bad acid rain forming components. So coal got a reprieve. We brought back coal and we weaned ourselves off a little bit of the oil, and we started to build more nuclear power plants. Now, if we fast forward and look, here we are 1850s, 1900, 1940s, 1980s. Here we are in the 1990s, right? Now, I was curious, so I went ahead and looked, where are we now? Well, here we are in 2005. Now, I know that's not now, but that's coming. We had now really started to burn a lot of coal again. 50% of our energy in 2000 was coal, right? Fossil fuels. And we had a lot more nuclear, and we were cutting way back on petroleum because we didn't want to have it coming from the Middle East. Since then, we've done a lot of work in the Gulf of Mexico, and we've got lots and lots of oil rigs, and we learned that if you simply pierce the crust of the earth in the ocean, the sea level will push the oil out. It doesn't have to be pumped. So oil is now king again. So I was curious, so I looked up a little bit ago what are the energy sources in 2019. Fossil fuels still make up 63% of our energy. Natural gas 38.4, coal 23.5. Petroleum, we don't get a lot of energy from petroleum, not anymore. We're burning fossil fuels. Most of us in the Midwest use natural gas. On the East Coast, they might use heating oil. Nuclear is 20% of the energy nationally. In Illinois, nuclear is nearly 50% of the energy that we use, which is why we spend a little time talking about nuclear energy in our class. Renewable energy, the stuff that's actually we like, hydropower, wind, and all that stuff, not a big contributor. Right now it's about 17.5%, right? Biomass, burning wood and those other crops, that's just a mere 1.5%. Solar, barely doing anything, 1.8%. Geothermal, 0.4. All the schools, the new schools have added geothermal. It's incredibly efficient as it takes the heat that's trapped in the ground. From the middle of winter to the middle of summer, if you go underground, the ground's between 52 and 55 degrees Fahrenheit. So you can harvest that cool or harvest that heat, depending on summer or winter. That's how geothermal works. All of these ultimately get their energy from the sun. The sun is the ultimate source of all these energy sources. In terms of energy transition, excuse me. Excuse me. We look at this, we might have a fan because it's warm in our room where electrical energy is transferred and changed to mechanical energy. Then we might have to turn on a light bulb to do our homework at night, where that electrical energy is converted to light energy, which is then ultimately converted into, if you've got one of these really kind of cheap old school lights that's a hot filament bulb burning on me, thermal and radiant energy. Then maybe you got to sharpen your pencil so that electrical energy is converted to mechanical energy. And then you got to stay up so you make your coffee where electrical energy is turned to thermal energy. All of these transitions occur. I hope that helps you understand energy a little bit better. Later on, we'll talk about that all substances don't transfer energy or heat equivalently, and we'll talk about that in calorimetry. So this is not going to be anything you need to worry about at this point. All right, thanks for staying with me. Thanks for listening. Hope you have a good day. Bye-bye.